Today we will learn about a single slit interference pattern. The single slit interference. Interference. So in the last video we have covered a double slit experiment and that looks logical for interference, but how light can interfere from a single slit? Only one gap. So let's understand what is the problem here. So what we were doing in a double slit experiment, we were drawing something like this. So we assumed, put our compass here, and we started drawing secondary wavelet from this single source. And then we understood that as we draw, we are getting some points of interference. These two wavelets are interfering with each other and they'll be adding constructively. If I draw troughs also, I will get destructive interference also, and I will get a pattern. So that makes sense. But what about single slit? How it can be, right? So we have ignored some fact here. When we were doing this derivation, we only thought that through this gap, only one single source will be there. Do you think that will be the reality? So why single slit diffraction is happening? Why we are getting interference pattern here? So let us understand. So when we are having a single slit like this, let's say this is the gap, and I'm seeing it by magnifying it so that we can see this gap as huge, right? It is not in real, but we are just zooming in. So what happens is the light is coming through here as a wave fronts, right? So these are the crest I am making, right? So this will hit here, right? So this will be cancelled out, this will be cancelled out, and the center one will pass through, right? Because this can go, it has a gap. And now let us remember Huygens. Huygens says you have ignored in the double slit experiment that there are multiple points on this wavefront. You have only considered one. But in case of single slit, that comes into the picture. So I will draw one here, 1 point here, 1 point here, and I can draw as many I want. I can zoom in more and I can make it 10. It'll be infinite points here. And every point will start creating its own secondary wavelet. Remember that. And that is what is happening. So this is the wavelet, secondary wavelet created by this guy. Now this guy is also on the same wavefront. He will say, I'll also do that. So he also is creating its own wavefront, right? And the third one will not remain behind. He will say, okay, I will also. So again, we are getting some interference pattern, right? I can draw the troughs also, how they will go, and we will see constructive and destructive interference. And that is the reason we will get some pattern here. Will it look similar? We will see the real picture, but let's cover the reason and let's read some theory. So when wavefront passes through a slit, single slit like this, all points on the wave creates their own secondary wavelets. I've shown it 3 here. These wavelets interfere with each other. Yes, see, they are. And we get interference pattern. And remember that we ignored this effect in double slit experiment. We only drew from a single slit only one wavefront. We were doing like this. One wavefront, one particle, 1 point only is creating the secondary wavelet. We did it like that. But now in single slit, we will factor in. Now you will be wondering how it will look like on the screen. Will it be similar to double slit experiment? Let's see that. This is the pattern which we will see. Can you note it down? We are getting bright fringes, we are getting dark fringes also, and then it alternates as they were doing in double slit experiment. But can you see one big difference here? One big difference is at the center, see this broad, let me use a different color, this broad fringe. This will be called what? It is at the center, right spot. You guess the name right, we will call it central maxima. Central, let me correct the spellings, central maxima. This is the highlight of single slit experiment. This guy, because look at its width. Look at this, tinier than this. And then you can also see the brightness is also going down. And in this derivation, in this video's crux is to how to find this width. How to find width of central maxima. And for that, we are going to do something different. We will not look for bright fringes. This time we will look for the dark fringes, this one and this one. And if we know the position of them, if we know the distance, don't you think that will make distance between them, let's say x, that will be the width of central maxima? So that is the change in this derivation, that we are looking for destructive interference. If we get those points, if we are able to get that distance, we will be able to calculate what will be the width of central maxima. So let's try our derivation. So let's start. So let us derive the expression for width for central maxima. And Please follow along. We have seen the videos of young double slit experiment, how we found the fringe width there. Similar steps we will do here. So in that, we saw the practicality first. Like, so how much is the slit width? So my slit width of single slit, which I am assuming is 0.1 mm. You know, this is not the difference between two slits, right? In Young's, it was distance between two slits. This is width of a single slit. Now, do you know how much this is? You're right. In your scale, the minimum line, this with only one line, if you count it, how much it is 1 mm. And I'm talking about 1/10 of that. So let's be practical and see our experiment from zoomed out version. So let me draw a single slit. So like this, and I'm going to draw a single slit. Okay, and remember, I'm zoomed out. I'm zoomed out. We did the similar step in our previous derivation of Young's double slit experiment. So follow along. So we are zoomed out. I will draw a single slit here. Is that it? Yes, 1/10 of a mm. So that is what you will get. Like single slit. I'm just showing it by a dot. And now I'm getting a pattern here, right? So let me put a screen also. So it's our screen where we are observing our pattern. So I will try to draw, yeah. So I will try to draw the central maxima. So that will be in front of the middle point of this slit. Now we can't differentiate, but you can just follow along around. That will be, we can just follow this line and we can reach it here. So this will be my central maxima. Yeah, and is it like this one I want to do because this has more width? That's what we are interested in. It's huge as compared to others, right? So this is the width. So this is the central maxima we got. In front of middle point of this slit's width, we will get this, and that will be symmetrical on both the sides. Now we will get a dark spot, and after that we will get a brighter spot as we saw in the diagram. So let me draw darker spot like that. There's no light here. Destructive interference is happening. And what we are interested in is finding this. We will put these two dark fringes. And if we are able to measure somehow what is the distance between them, we are getting this central maxima's width. And let's say, I'll use a different name, x. Let's say it is x, right? So this distance is x, okay? Okay, so now come to this point. Why this destruction is happening? Why destructive interference is happening? Because we can say the rays coming if 2 points, the topmost point of the slit and the middle point of the slit, you can't see it properly, I understand, but imagine that we are able to see it, then they are coming here and interfering with each other destructively. What does that mean? It means the path difference should be lambda by 2. And we have covered that in previous video, so please revise that. For destructive interference, the path difference should be lambda by 2. And let me recap it faster. Let me recap faster. So there is one wave going like this, and the second wave I'm going to draw like that. Okay, so if they'll add up, they will cancel out each other. See, the crest is matching the trough is matching the crest. They will cancel out each other's effect. So what is the path difference? Can you see the above one, this top one has traveled more distance, right, than this one? So how much is the difference? This one, right? So if complete is 1 lambda, this will be lambda by 2. And I'm coming from here. That's why I'm saying if it is we are finding destructive interference here, the path difference must be lambda by 2, right? So agree on that point? Okay. Now let me draw two lines here which are meeting here, right? Which we are meeting here. So I will of course approximate. So I'm taking the dot's top part and I'm trying to draw like that. So this is, I'm representing a wave coming here and doing destructive interference, and the second one from the center of the dot. Just want to tell that I'm taking from the middle part of the slit. Okay, and you can see they are almost parallel, right? It is looking like they are the same line, right? And now the same exercise which we did. So if I draw this reference line, after drawing this, you should be able to see one triangle. Can you see the right angle triangle? So if this is 90 degree, can you see the right angle triangle? Clearly, very clear, right? And let's say this is theta. So again, the same thing as we did in the last experiment. Can you give me tangent theta? Do you remember what is the tangent theta? Tangent theta is a perpendicular divided by the base. What will be the base? It will be d, distance between the slit and the screen. And what will be this length? What will be the perpendicular? See, the total is x and it is midway. That's why I'm taking distance from the middle of the slit. So this will cut this in half. So this distance will be x cut in half, x by 2. Right, so we got the perpendicular, we got the base. So can I say it'll be x divided by 2 divided by d? So can I simplify also for you? X divided by 2d. And that is what our tangent theta. Can you see the similarity which we did in Young's double slit experiment? Similar way, we are just finding one triangle in the zoomed out version and calculating a tangent theta. This will become our first equation. Now, let's discuss this. What will be the path difference? Path difference will be lambda by 2. Then go on, calculate here. Oh, it's very, very close. I'm not able to see the diagram properly. So what do you want to do? We want to zoom in so that I can see the path difference very, very clear. So now, zoomed out to zoom in. Okay, let me show you the slit. So the slit is like this, and let's say middle point 1, 2, 3. Middle point comes here, 1, 2, 3, and I will start like that. Right? So this is a slit. So I did it so that I can get a middle point very clearly. So we need one ray. So as we were doing from the top, but now we are able to see the difference, right? It is not a single dot. So we'll be able to draw them properly. So this one. And what is the middle point? Middle point is this, right? From where we have taken this line, right? In front of that, we'll get central maxima on the right. So this point is the middle or midpoint of this slit. So second ray will go from here, remember, not from here. So I will draw a parallel line from here. And now we can see the difference from the dot. It was very difficult, but you're still able to understand what is happening. So now this is the second parallel line, and they will go on and meet destructively. Okay, so now can you calculate the path difference here? So the similar exercise, we will drop a perpendicular like that on this line, and we will say, okay, this is the path difference. After this, they are covering the same distance, but this is the path. So let's say width of this slit is, we have taken 0.1 mm. Let's have a general name for that, like W if you have W like that. Right? So this is the total width. So can you see one triangle here? If I just make this dotted lines join, right, for my reference, you are able to see another right angle triangle, right? And remember, similar exercise, this is theta, then this will also become theta. So what we did in the last one, if this is theta, this will be 90 minus theta. You add up them and you'll find this angle will also be theta. So now we have one triangle, right angle triangle. Oh, this is the path difference. This is the path difference which we are looking on. This is the path difference. And what about this? So the entire width is a W, right? So this will be W divided by 2, right? Now, can you guess the next step? Yes, the next step is calculate sine theta. Now sine theta will be perpendicular, which will be front of the angle. That will be our path difference. Path difference. And divided by hypotenuse. Hypotenuse will be this longest length of this triangle. So that will be W by 2. So I will do like this. What will be the path difference for destructive? It has to be lambda by 2. Remember, it will be lambda by 2 only. So lambda by 2 divided by W by 2. Oh, I can cancel out these 2's. So I can say the sine theta is coming as lambda divided by W. And here comes my second equation when I'm zoomed in. Now our derivation is done. We just need to compare and do small angle approximation. Let's do that. So here are two equations which we got, one from the zoomed out version, calculated tan theta, and zoomed in version where we calculated sine theta, right? And now we will do small angle approximation. What I want to say, for small angles, tangent theta will be equal to sine theta, which will be equal to theta, we can say. So now if these angles are same, I can put theta is equal to x divided by 2d, and I can also say theta is equal to lambda by w, so they must be equal. Or x by 2d should be equal to lambda by w, right? Can we go further? What we wanted to calculate? We wanted to calculate this x, right? We were interested in this and we are getting it here. So I will keep x at the left side because I am interested in that. This is the width of central maxima. This guy, total x, will be equal to 2 into, let me put lambda first, then d, because this will get multiplied here, and then divided by width. And this is what the expression which we were looking for. This is the width of central maxima in single slit experiment.